Thank you for the introduction. And so, what we want to speak about standard are special type of partial differential equations which give rise to various geometric structures, and how these structures can be used either to classify those equations under certain circumstances and some specific dimensions, and how from these structures a new, more complicated geometric structures can be derived, again leading to either applications beyond the equations themselves or back to the equation. And because the theory of Monge-Ampère equations is already quite well developed, and there are many results regarding symmetry, and for example, when one equation is equivalent to the other, doesn't imply about the geometric structures, whether they are preserved under the symmetry or not. One can also ask the question how we can use the theory of Monge-Ampère equations to further study the geometric structures, which one can see, of course, as being completely disconnected with the equations unless we need to connect it. So first of all, I will introduce the equations themselves. Then I'll show how we can treat them geometrically by differential forms, either on the jet space, but we'll be mainly on the first jet space, but we'll be mainly interested in the subclass of these more general equations, and we will speak about symplectic Monge-Ampère equations, which are described by differential forms on the cotangent bundle. I will give explicit examples in 2D, 3D, and 4D, and I'll show how the geometric object that we are interested in can be derived from those, and mainly we'll be interested in so-called Lee-Chagrin roots of metrics, which again can be derived from some subclass of symplectic Monge-Ampère equations. And then Standa will show some of the computations that we have done recently, which give us new information about the equations, and also we have found solutions to vacuum field equations in 4 dimensions for these, regarding this Lee-Chagrin roots of metrics. Okay, so first of all, what is a So, loosely speaking, Monge-Ampère equations are second-order PDEs, which are given by.
Hi.
Hello.
Hi. Sorry to interrupt you. Just I cannot see the left side of the blackboard. I can see only the last 3 letters before Ampère.
Before what?
Ampère.
So like this. Here.
Yeah, exactly.
Exactly. Yeah. But then no. First, I want to get all the details. Yeah. I already made one.
Something like this?
Yeah.
Focus. Giacomo, can you see now?
Yeah. Yes.
Is it in focus?
Is it focused?
Yeah. Yeah. Yeah, should be okay now.
Okay, so let me start with the case which will be most interested in this talk, and this is the case where the smooth manifold we want to consider as a space over which the equation is 2-dimensional. So the general case of Monge-Ampère equation comes from this type of construction, where this is the first jet of functions over M, and we want to be restricted like this, where we understand that T star is somehow in the J1. Okay, and now whenever, so this is a natural projection, whenever we consider a smooth function, we can take differential and view it as a map from M to T star M. Okay, so this is like choosing a section of the bundle, and if we have a section of the bundle, we can consider the pullbacks of differential forms of the bundle. I mean, over T star M. So now pick a. If we are in the dimension 2 of the base manifold, we want to pick a 2 form, and pulling back this 2 form on M. So this guy will be a 2 form on M. And since M is 2-dimensional, it will be a top form. So if we choose a volume form M, then this will be the multiple of the volume form. And if we do this equation, then we call this a symplectic Monge-Ampère equation to the right. Okay. The most general symplectic Monge-Ampère equation, if we pick coordinates on M to be, say, x and y, then the most general symplectic Monge-Ampère equation in 2 dimensions looks like this. X, where this denotes the double derivative with respect to x, there, f is x, plus 3 y. Zero, of course, that's that.
So it is the unknown like this.
And that is the unknown, yes.
And A, B, C, D, E are functions.
And A, B, C, D, E, A, B, C, D, E. So we want to consider the corresponding form. In this form, the coefficient will appear, and that will be understood as function on T star M, right? But once we pull it down the form, produce the equation itself, the coordinates on T star M, which will be like x, y, like base coordinates, and final coordinates PQ. If you pull back those, so in this case, A is a function of x, y, p, and q. But if you pull it back down, those will be functions x, y, fx, and fy, because those coordinates p and q will be understood as a derivatives, partial derivatives with respect to x and y. Okay. So this is the most general symplectic Monge-Ampère equation depending on 2 variables, x and y. And the corresponding differential form on omega 2 T star M will be what? Will be following guy. A dp dq. As I said, notice that here I use the same letter, but actually this is the precomposition of A with the chosen section of the bundle. Okay. So A dp dp dy plus b dx dp minus dy dq C x dq the dq plus b dx dy. The choice of the volume form will, in our consideration, be done with the correspond to the choice of symplectic form, which naturally lives here. So when we want to describe Monge-Ampère equation via differential forms, we first need to pick the volume form, and we pick the volume form by choosing the symplectic structure. And the symplectic structure in this case is dx dt dy q. Okay. So this is the setup that we use as a beginning for deriving the other geometric structures. So first of all, we may consider so-called Pfaffian, which is given implicitly by this equation, and we call the Monge-Ampère equation non-degenerate if the Pfaffian is non-zero. Yeah. Why are we interested in the non-degenerate case? Because the non-degenerate case provides us with geometric structures which are non-degenerate as well. Yeah. And what are the structures? So, for example, we can have almost complex, possibly integrable, almost complex structure, and we can have almost product structure. In this case, on M. And so what I mean by this is an endomorphism of T star M such that it squares either to +1 or -1. Okay? And how it is described? Again, by an equation which is like alpha x bar omega. I'll write it. Omega.
So what is the endomorphism?
And the rho is the endomorphism, which is either a complex structure or product structure almost. And why I introduced the Pfaffian? Because the Pfaffian. So okay, that's it. And we have this. So we obtain the almost complex structure in the case of an alpha B.
This third color is not so good.
That is not visible on the screen, or?
Yeah.
Nice, sorry. So red one? Yeah. Better? And almost productive if the Pfaffian is negative.
But this is some additional compatibility structure with omega and rho. I mean,
symmetric, for instance, if you do this?
Alpha or rho alpha?
Alpha, if you define alpha in this.
No, alpha is given. Alpha is given,
What is
omega
not-
is given, and what is not given is rho alpha.
So this is a condition for rho alpha.
This is an implicit equation of rho alpha. Okay? So we can define alpha like this, and if you go into the matrix notation,
So it's, well, I mean, it's not even it's possible to do it for any alpha. I mean, omega is canonical, it's the symplectic structure, but alpha, you could imagine having many different alphas. You have a lot of constants there. It's not clear to me that this is even possible for generic choice of alpha.
so this guy will be well defined if this holds. Okay, and the alpha is so the alpha can be as generic as far as this condition is satisfied.
Because if I have, yeah, it looks a little bit like the relation between the symplectic form and the complex structure
Yes.
in Gaussian geometry.
Mhm.
That's certainly not possible for any
Well, of course,
complex manifold.
It doesn't always-
You have to have a Hermitian metric that works.
it doesn't always give rise to Taylor structure, but it can give rise to Taylor structure.
I'm not asking about Taylor structure here. I mean, I'm asking if it's because if you're talking about Taylor structure as an analogous situation, you have a complex manifold, you have a complex metric. That's not enough.
But so
the
far,
fact that you want to have the compatibility between the Taylor form and the complex structure and the metric,
but
it's
so
not
far,
really a condition.
so far we have no metric in the game.
This is just an analogy. The metric is omega.
No, omega is not a metric.
Analogous construction. If I'm using Taylor geometry,
But isn't it just a consequence of the fact that both alpha and omega, if you think about it as matrices, invertible?
Sure. Yes. Which is associated with the non-zero factor.
Yeah, that's the normal.
Yeah.
Exactly. You can map one together.
I'm just saying that this is what you do in Taylor geometry, and this is certainly not something that you can always do if you have. I mean, what?
You mean like if small omega is like alpha, or?
I'm just saying this is a formula which made me think about Taylor geometry. Looking at this made me think about Taylor geometry. This is certainly not possible for any metric.
I agree.
So I'm saying my only question is this, are there some similar restrictions here like there are here? This is not possible to do for any metric. Is this possible to do?
And you are, I guess the difference is that j's have to square to -1, but here there's no. But there's no condition.
Squares to -1.
Yeah. So that's the extra condition which there's not a rule. There's no
But this is
condition.
conditional rho. Rho is an almost complex
So
structure.
if you want rho to be an almost complex structure, you do this one.
And it needs to square to -1.
Okay, so yeah, but
No, if you satisfy this,
yeah.
rho automatically is square to -1.
Okay, fine. But that what you're saying is not a difference. It's the same.
Okay, so you're saying that the rule have to square to -1 automatically.
Yeah, if this is satisfied, then rho square to -1 automatically.
And then it's
If
square to
this is
-1.
satisfied, then this guy will square to -1.
Why?
Well, if I express, so you have to do a computation, right? If I express this equation in matrix notation, then I'll obtain rho alpha equals to 1/square root of alpha. And now, what you will see here is a multiplication of anti-symmetric matrix corresponding to alpha and the matrix corresponding to omega s. This will be written here. B minus A O 0 minus B C minus B B 0.
Just use.
Oh, yeah, sure.
Not this specific.
So we have this. And if you compute the square of this guy, what will happen is, so let me write it here. Okay, so that's what happens. And that's why the sign of the Pfaffian governs the, if alpha is invertible, then which amounts to Pfaffian being non-zero, and if Pfaffian is positive, then it governs whether the structure will be almost complex or almost perfect.
So maybe the difference is the omega is really fixed.
This guy is fixed, yes. This guy is fixed.
Fixing the metric.
Also, omega is antisymmetric on the metric. It's the metric at work.
So it's not completely, I mean, like this kind of story can be introduced, but not in this way.
I'm sure it's not exactly. I'm just saying, if there are any additional conditions,
For
existence,
existence,
it just works.
yes, exactly. Condition for the existence of some structure, condition of existence of specific type of structure. Yeah, I mean, in this context of almost complex or almost perfect. That's right. Yeah. Then we can say a bit more in this case, and we can say that alpha is integrable, and so once again, maybe the way to or what I want to say, the point is that the omega is fixed. Okay, we choose a symplectic form, and then all our equations will be only dependent on the choice of alpha, and vice versa. Right? So, of course, rho alpha depends on alpha and omega. The method that I will define will depend on alpha and omega, but omega is fixed. Of course, if we change the omega, we can proceed similarly, but there will be some appropriate changes. Yeah. So rho alpha is integrable only if d of what? No, it's not the closeness of alpha. It's closeness of alpha being normalized. So it's like this. I'm not sure there's square or not sure about the denominator, but the topic is
Square root, right? Because you want it to.
yeah.
After
So I guess it doesn't make sense. I think you want to keep it real, right?
Oh, yeah.
So it's probably not really.
You're an absolute value in this curve.
Yeah, sure. It should be everything. Here as well. So we want to do everything, we want to keep it real. Yeah, not that one cannot consider the complex case, but what we will be dealing with is just the real world, so to speak. Thank you. So if, of course, if half is constant, then we see that the integrability condition amounts to alpha being closed. Yeah. But this is, of course, not equivalent. Yeah, the closeness for general. Okay. So I guess now is a good time for examples. So 2D, and we can of course consider this as a 3D case as well. So this guy. Yeah. So this is a very simple one. We can provide a form dpdq minus x dy. And if you are interested, we can very easily show how the equation arises from this form. Are you interested, or is it clear?
I think it's good to do.
Yeah. So if we want to, if we pick f, of course, the choice of f is sort of arbitrary. Yeah? We do not say that if this f has to satisfy the equation. Yeah? It's just some f, which corresponds to the choice of the section, so that we can move it down the form. And what we get is d, and the p's and q's are substituting the relatives. Let us assume that the going form m has been chosen as the x dy, right? M is still two-dimensional. Okay. So yeah. So like 3D, because we can consider the same equation in 3D as well. Yeah. But now I'm doing this case. Yeah.
Obviously by introducing step.
Yeah. So this is just like two examples at once. And then focus on.
And then alpha will become a tree form.
Exactly. If you want to consider Monge-Ampère equations or Monge-Ampère equation depending on more than two variables, I mean, the number of variables in the Monge-Ampère equations equals the dimension of the base manifold equals the n in the n form we consider alpha to be. Yeah. So in general, alpha can be. And there is plenty of these guys. If n has dimension n, because this term is 2n dimensions, so we have plenty of choices. Okay. And I'll speak about the choices a bit more, but not very rigorously, just to say that there are some issues that we need to deal with if we want to represent the equation by differential form. So what happens here is x dx plus x y, and it becomes very quickly very obvious. So we see that thing. So this guy is equal to 0 if and only this Monge-Ampère equation is satisfied. Okay. Now, about the issue with representing the equation by differential forms. How is the time? Yeah. 14:32. I should be faster, right? Because so if we want to actually, why do we want to do that? Yeah? Because if you consider the equation, we might not be interested in solving the equation itself, but only in the sort of geometric content of the equation, which is sort of given by some geometric structure of the tangent bundle and the form that defines the equation. But we can describe the same equation by different differential forms. In 2D, it is not that obvious because all the two forms behaves nicely in a certain sense. But if we consider 3-dimensional or 4-dimensional case, I mean, like just going just 1 dimension up, the forms that represent the equation contain some sort of ambiguity. In other words, there might be parts in the differential form itself which, if pulled back down on m, produces a pseudo equation which is satisfied by every f. Yeah. So this is some sort of ambiguity in the presentation of the equation by the differential forms. But we can get rid of it by requiring that alpha dash omega equals 0, and this is the effectivity condition. Alpha. And there is a very nice theorem by Valentini produced in 80s, really, or 70s, quite some time ago, that every Monge-Ampère equation can be represented by a unique class of effective forms, and the sorry for the naming here, but the representants of the effective class are I mean, like, two guys are in the same class if they differ by a multiple of a smooth non-vanishing function. Yeah. So there is a lot of ambiguity, but we can get rid of it in a sense. And sometimes the geometric objects that we are dealing with are independent of the choice of representant in the effective class, but sometimes they are not. But we can always pick any differential form which produces the equation, and then really algorithmically compute the effective part of the differential form. So computationally, you can always go to the case which is unambiguous in a sense. Okay.
Okay, so you're saying that if you have an alpha,
If I have
there is a representative which is different from the initial alpha by an overall non-vanishing function.
No, that's not what I'm saying. Okay, I'm saying that take an alpha. Yeah, this alpha produces equation in, let's say, this way. Yeah. Then I know that there is another form of the same degree which gives you the same equation and satisfies this condition. And this form is given uniquely up to arrow scaling by a non-vanishing function. That's what I'm saying. Yeah, that's what I'm saying. The difference between non-effective guy and effective guy can be quite nasty in 4 dimensions.
Of course, yeah. This condition is stable on the
Yes, exactly. That's where we see the class. Yeah. Or that it is class. Okay. So. Example number 2. So we will be mainly interested in this guy, but in a more general setup, which looks like essentially kill ABC and focus on this guy. And it has quite special properties. I mean, like the geometric structure that derived from this guy has quite special properties. Maybe under some conditions on D and E, depending on, for example, what we want to do with the geometric objects, whether we want them to satisfy some further relations and so on and so forth. Another example, so would be second heavenly lines. And it looks like this. So now this is a 4D, yeah, 4D equation. And we have like x, y, z. Let's say x, y, z, w coordinates on the base, and let's say p, q, r as the fiber coordinates of the cotangent boundary. Okay. Minus x, y squared plus x, z plus y w is 0. And the differential form, the deals this equation looks like this. Is if you start with an equation to find some differential form which represents the equation is fairly simple usually, but to find the effective one is more difficult and requires patience. Rather tedious than well, it's rather tedious work than the difficult one. So it looks like this. Those who are interested in how effective part of this form looks like, I suggest to after the talk to come see my computer where I have the form, but it's quite nasty guy. Yeah, it has like coefficient like at some part it's coefficient like 1/28 or something like that. Yeah, it's you wouldn't definitely guess it. Yeah. Good. And so just to say a few words, this heavenly equation of Levinsky comes from a self-dual relativity, so it's quite an interesting equation. There is also first heavenly equation of Levinsky, which is also Monge-Ampère equation, symplectic in fact. We have ground equation, Hussein equation. Those are also symplectic Monge-Ampère equations, depending on 4 variables. And to say an example of a Monge-Ampère equation which is not symplectic, we can consider the Klein-Gordon equation. Yeah, that would be a non-symplectic Monge-Ampère. If we want to deal with this kind of equation, we cannot restrict ourselves to coefficients A, B, C, D, E, which depends on x, y, p, q, but actually on u as well.
So you wrote it in the opposite order. The first term is connected with the f, y.
No idea in which order it is. I just know it works. Yeah, I'm not saying that this comes first.
You want to write it as an x, y, z, w in terms of the x, y, z, w form. So the first one will just give you an f because q is f y and you get the w derivative. So that would give you the linear term in f y w.
Yeah. So as a w, it would be this guy. This guy would be this guy.
And then the second term, you would get
This guy probably. I guess this guy.
z derivative of x.
Exactly. And this guy, because you see, you have 2 terms to correspond to this guy. Yeah.
So you completely switch.
Yeah. But you know, because you start with an equation and then you come to differential forms and you work with differential forms. And so in this sort of ideologies, you
As a pedagogical example.
not the best choice. Yeah. But you see, I have it. I'm like ordered as x, y. I mean, like I have ordered it this way. Yeah, always. So x, y is fine. So from a lexicographical point of view, I agree. It might be a little bit misleading. Good. To see some I suggest I will neat examples and various structures we can get and jump to the case of the symmetric linear form.
So, but the effectivity of this form
Of this one,
no, sorry.
this is not effective.
Oh, it's not.
As I said, the effective part of this guy is quite complicated.
Oh, I see.
Let me, it's fairly quickly, so just for the sake of completeness, I will not write it down, but I will, come on.
So which part is not?
I'll show you.
P is gone.
So,
Or so Z, no.
oh yeah, the second Levansky has quite nice, quite nice effective part of the alpha. I mean, like we say, effective part, yeah, but it's completely different differential form. Yeah, it is effective part in the sense that that alpha can be written as alpha 0, the effective part plus something. Yeah, so so the terminology might not be the most convenient sort of sense. You can check what it looks like. So these two guys represent the same equation, but only this one satisfies the condition alpha beta is 0.
Yeah.
I will not pass the books or I will pass the computer, but and for the first Levansky, it's much more complicated. Yeah, the effective part is much more uglier.
What about the row complex or product structure?
And what about it?
What is it? What is it good for?
What is it good for? So,
how does it look like? Is it a complex structure?
So, in general case, rho alpha looks like this if we use the matrix notation. Okay. So whenever you pick specific equation, I mean, like in this 2D case, when you pick specific guy, it will just follow from this. The Fatkian you can compute very easily, and you have the matrix.
Right. So now we take that structure and either get holomorphic combinations of colored coordinates, or divide them into two pieces in some sense. In either case, I can. So does that tell me anything? Is it useful?
Well,
is it surprising? Is it trivial? You say, well.
No, for example, you might be interested in the classification of all complex structure, or almost complex structure of this star, right? For example, and you can do this by classification results from the Monge-Ampère equation theory. For example, I'm not like saying let's now use rho alpha and get the hell out of it. Yeah? So we have just some nice geometric structure that are associated to the specific type of equations.
But it's not like something trivial. Well, the base coordinates are separated from the fiber coordinates and the structure. That's always the way it is. That doesn't look like it's some interesting non-trivial thing. It does contain some information. It's not a trivial thing.
Sure. I'm not sure about the question.
I'm just trying to you define rho and then you just started calculating, but you didn't use it.
Oh no! It was just because the idea of this talk was to introduce Monge-Ampère equation and show that there are various geometric structures associated to those equations, and we are not particularly interested in this guy, in these almost complex almost product structures. And I don't say it's not an interesting subject to study, yeah. But I don't say that. I don't say it's not. I think it's quite interesting. I used it in my previous results regarding generalized complex geometries, yeah, and generalized product geometries. And those guys are exactly the building blocks for that. But we are interested in the metric structures, yeah? Okay, in this talk. And so this was just an example. It's similar as you would ask me, what do you do with this kind of equation? What do you do with why this kind of equation is important?
Yeah, exactly. So I would, I would
Just give
count an example also for this an interesting non-trivial role. As you said, this is an interesting non-trivial equation. I think.
Sure.
So is there some example?
Yes, there is, of course. And I'll give you. So let us consider the following case. Let us consider the following system of equations. Where what V is the velocity field, this nu is the viscosity, which we understand as a constant, and P is the pressure field. And these two equations, well, so I'm not the one who is studying these equations here. But what should hold is that those two equations governs 2D incompressible flow on R2. Okay?
Well, actually, any dimension with this.
Sure. But we are sure. In 2D, let us fix the case to 2D. Then from these two equations, we can actually derive the following condition that
Okay, so what is that?
and F is sorry.
Yes, it's maybe solving the divergence of D.
Yeah.
In terms of
So this should be the stream function.
yeah.
Okay. And here we have flatness. Okay. In this case, it is 2 delta P. And we can say that rho alpha.
So in this equation, delta P is like the E, the constant.
Yes, exactly. Yes, exactly. Yeah. So imagine ABC equals to 0, D equals to 1, and E equals to 1/2 delta P. Yeah.
Okay, so now I have D. It's only D and D. Yeah.
Yeah. So we have this guy, and this is a. So again, the general results hold. So if this guy is positive, this will be almost complex fraction. If it's negative, it's not. It should be like negative. So we assume this guy to be positive. So we can result, and this will be an almost complex structure.
Okay, and it combines now the first and the last, the second and the third together. So X is combined with the momentum of Y. Is that correct? Or
Once again, what was the question?
what is the symplectic form?
The symplectic form is the same as the one.
Yeah, so it doesn't combine X with its momentum. It combines X with the momentum of Y. it's not like a, you know, if you're talking about canonical things, there are.
Oh yeah, you mean like the symplectic form?
No, not the symplectic form. This guy
This rho alpha, yeah.
is different.
Well,
Right, but it's, those are not the same as you would get from the symplectic form. The symplectic form also combines things with each other, but this guy combines different things with each other. Okay, so can you use that in some interesting way, or what does it tell you? What it gives you some kind of geometric structure of this space. So what does that tell you? How can you use
So, so now I want to refer to work of other people, yeah, to the work of Ayn Rustov, Volodya Rubtsov, Martin Wolf, and what they do is in this specific setup, they are able to define if delta p is constant, if this guy is constant, then they can define Kähler structure for this equation. And then they use the Kähler structure to somehow study the properties of the flow, which these two equations should describe. Yeah, that's sort of a motivation for us to be interested in further study of, like more abstract study of the geometric structures. Of course, the applications to us are interesting, but at this moment, we know there are useful applications in the, for example, methodology, and we just thought also, I didn't get to the metric structure yet, yeah, but we know that not only the almost complex structure can be used, but also the metric one, and then from the metric structure, the same authors that I mentioned a minute ago, they are using the scalar curvature to distinguish between, the sign of the scalar curvature to distinguish between regions in which vortices of the flow sort of survives around some stability points, and the regions where the sort of vortices vanishes in time. Yeah. So that was our key motivation. I wanted to.
Okay, yeah.
No, like those are reasonable questions, yeah, but.
No, but this is what I wanted to see.
Yeah.
Yeah, a nice example.
Yeah. Good. So now the last thing I want to introduce, I believe, is the following object. G alpha is 1, is 2, and I will need a bit more space. Sorry. But this is just insertion operator. This is 2. Omega, and here I have dx/dy. Yeah, so M is 2-dimensional. This is a 2-form always. This is a 2-form for the 2-dimensional M. And so this is a 1-form, which is 2 with the chosen volume form, and upstairs is a 4-form, and here we have 4-form as well. So what we want to say is, if I evaluate whatever this guy is, if I evaluate at xy, the number that I get, or the function that I get, is the multiple of the chosen volume form this way, yeah? And obviously this is symmetric guy. And the linear, it looks, the matrix looks like that.
But this works only on two dimensions.
Yes, exactly. So everything we did was for m equals 2. We can construct G alpha for m equals 3, and we are just so far we are fixed on m equals 2. Yeah. The matrix of this guy is following.
So what's the relation between the matrix and the
What is the relation between
row? What is the relation
between G alpha and rho?
Yeah, the matrix. Sorry, yeah, the matrix.
I mean, like a priori, no relation. I mean,
It looks
like
like, because alpha is really omega with rho inserted, so you're going to get like sort of omega with with rho inserted divided by omega with omega.
but notice, for example, notice that here I do not assume Pfaffian to be non-zero. Yeah, the condition for G alpha, let me write the matrix from G alpha and I'll comment. The condition on G alpha to be a metric, so non-degenerate, is simply because its determinant is d to the power of 4, so the condition is d not equal to 0. So if we forget about all the other geometries like rho alpha and whatever we can derive from the geometric content of the Monge-Ampère equation, we focus on this guy, then the only condition for alpha or the equation itself is that d must be non-zero, and then we have a metric. Yeah, to the m equals 2. Yeah, dimension of m equals 2. And I believe if I remember correctly what we discussed previously, this is the part where I let you take the slide forward. Maybe I'll erase it for you.
Okay. So now the idea was to just focus on this metric structure we have and try to find out the most things about the metric and use the equation if we needed to. Well, the idea was to maybe find some classifications of Monge-Ampère equations depending on the properties of the metric. So the metric depends on these A, B, C, D factors which are also in the equation. So if we say, let's see if the metric satisfies Einstein equations, then we find some equations on A, B, C. Then we will get a classification of Monge-Ampère equations for which this geometric structure is Ricci flat or not Ricci flat, and stuff like that. So we focus mostly on.
What's the signature?
Yeah, that was the first point that we wanted to see. So no, the first point was to see when it is a metric. So the determinant of this metric is quite nice. So if D is non-zero, then it's a non-degenerate. And the second question was to calculate the signature of this metric, which is sometimes used in this methodological application. But yeah, I'm not exactly sure about what is the exact application, but they do calculate the signature and it affects the regions of, I think, it affects the sign of the pressure or Russian.
So two-dimensional hardware doesn't appear in the system.
Yeah. But that's where they use Monge-Ampère equations to study this as far as you know. So first thing was to calculate the signature. So we calculated eigenvalues of this metric, and we get something like this. Then there's there will be four options depending on how we choose the signs. So I'll just write how it looks. And then we see four eigenvalues, and one will be plus plus, plus minus, minus plus, and minus minus. And then we have square root of 2, square root of a squared plus c squared plus 2b squared, 2b squared. Here remember that these coefficients are coefficients of the alpha and also coefficients which appear in the Monge-Ampère equations. Minus a plus c square root of a squared. Yeah, and here's the same thing as here. A minus c squared plus 4 squared. So the conjecture was that we also discovered when trying to plug in the various values of ABC, and which was conjectured by so is that the signature is always 2, 2. There is no possibility for non-degenerate. For if it's not 0, then it always has to be 2 positive and 2 negative. And so we try to prove this by also our method was to use like proof of concept.
Can you put the equation again so that I see what the definition of the coefficients were?
Yeah, no problem.
By the way, is there some geometric significance for this kind of metric? Or is it in some sense uniquely given for some conditions? Because now it just
Good question.
it just looks like a weird formula.
No,
without
it's actually not. It's not actually a weird formula. Consider that you have a symplectic form and a 2 from alpha. And now construct something as simple as possible, which is symmetric and linear, in a sense. From alpha and omega.
Yeah. A second look on it.
Oh,
No,
No, that was exactly it.
yeah, I was checking.
so you said you wrote to fx y r y x. Or
No, it should be the same.
Oh yeah, because on the level of the differential from the presented equation, you have b in front of 2 terms.
I can write alpha also if that helps. Maybe I'll have. I should have this minus 0.
Yeah, there's something like dx wedge dq minus dy wedge dx.
Yeah, exactly. dq.
Yeah, because until you treat yourself with the graph of the section, you not see what which part.
So yeah, about so this is the form which gives rise to this equation and in turn gives rise to this metric. And the first thing is that the signature is always 2, 2. So that was our first conjecture.
Would you write the method once?
Yeah, that's the.
He meant the definition.
Yeah, I meant the definition because
Yeah, sure.
I'm not really sure about how that converts to it.
Yeah, I'll write it in the notation. Radek. Yes.
No, your alpha looks like an A or an alpha cut in stone or I don't know, what is it? A, drawing A or?
I don't know how I'm supposed to write alpha. So
You start up here. Whoop, whoop. No, you don't have to do 2 lines. Let's start that. Like you see, you have to start from the right and go to the left. After I go down,
I guess you just have to.
I think we have to make some practice sessions.
Yeah. Yeah, so this, which is just instead of writing 2 terms, I wrote 1 and symmetrized in X and Y. So the way you would.
Okay, but you forgot the other, the omega.
After the
Or
second
the
operation.
Okay, so the way you would just calculate it is that you get this by plugging here dx, dy, yeah, and then you just plug everything in here and wedge it with omega and read off the components. So that's not a long calculation. That's a long calculation, but a very simple one. And so the way that we convince ourselves that this works is that because of you always have these plus and minus here, and the things in here and in here are sort of related in a sense that if you just plug in numbers, you would always get that one of them would be bigger than the other, and then plus or minus, you will never get, for example, for a positive eigenvalue. So the way we try to see that is that we try to find a choice of A, B, C such that A plus C would be bigger than this plus this. So if I call this X, call this Y, just to be short. So if it's bigger than X plus Y, X plus square root of 2 X. And then, yeah, we just solve this inequality. We just put this here and square the whole thing, taking care about signs. If the thing on the left is positive or negative, you do both options and then see that both give you the same thing. But it's a lot of writing. So if you just square this, then plug it back for what X and Y are, then everything here cancels on both sides, and the only thing that you are left with is 0 should be bigger than 2d squared, which you see that it is impossible to satisfy. So it is not a full proof that the signature cannot be for 0, but you can never get this to be such that if you subtract these 2 things, you will get something negative. So if that is the case, then you can never get signature for 0. That's so. Yeah.
And it's obvious that the second term is bigger than the first.
Yeah. Yeah,
There
that
should
should be
always at
some.
least one negative.
What?
There's always at least one negative.
Yeah, yeah. Yeah, and then if you work out, then this should be like comparable with these two. And the way we did it is that just try to see if these two can be somehow bigger than this, and you can see that that's not possible.
Why is the second bigger than this?
Perfect.
Oh, I made a mistake.
A
plus. So it's A plus. Okay.
Oh, no, yeah, so there's
A minus.
A
A minus here. And there's
Yeah, well, but yeah, there is some relationship between them, and we believe that the signature is always 2,
we know it cannot be 1, 3 or 3, 1.
so it should be only, yeah. And then the way we try to do it is that if this can be somehow like smaller than these two, then they could subtract from it and put something negative, but that cannot happen due to this. So the first two things we tried to work out for this metric was the signature determinant, and then we tried to see if it can satisfy Einstein equation. So what is the Ricci curvature of these things? Just calculating. Okay. Because if we are in 4D, which we suppose we are, we suppose that P and Q are just some normal coordinates and not ux and uy, then the Einstein equation is equivalent to just the Ricci tensor being 0. And yeah, computationally it is very difficult to compute with the whole equation, the whole metric. So we just focus on the case where A equals B equals C equals 0, which still is the most important case in terms of the applications. And we calculate this. We calculate the 10 independent components of this tensor and try to solve the equations. So we get 10 equations. I will write them in a shorter form. So 4 of them look like this. So if you imagine this metric with ABC equals 0, so it's identity times d over the octagonals, and d is a function of, and we are solving for this function. We'll try to see if we can solve the Einstein equations. We get 10 equations. So we get 4 equations that look like this, and they have then 3 additional choices where there is y, p, and q. So that's 4 equations. Then other 4 equations. Yeah, I don't want to spend time writing all 10, so I'll just write them in the short form. Then we get 3 times dx dy. 2 x y equals 0, and then we get additional combinations q and x, p and y, p and q, here. So that's 4 equations. That's 8 total, and then 2 of the equations are more complicated. Like q dp dx minus 4 dxp to 0, and 1 additional equations where yq goes to px and px goes to yq. So the same equation, but here is yq, and here is px. So that's 10 equations for one function of 4 variables, but it's not that difficult to solve them. The way I did it, I'm not sure if it's the, well, it's definitely the only way, is to just start with the first equation. I just solve this equation because there is only derivatives with respect to x. So you can actually solve it. You can solve it by, yeah, it's quite easy to see. 3/2 x. You can just multiply by some integration factor, which is 1 over dx. We get 3 times dx over d equals dxx over dx. Yeah, which both sides are derivatives of something. So this is logarithm of dx, this is logarithm of d, this is logarithm of dx, both are derivatives, and then yeah, you will just get that you have dx is d to 3/2 because it's a logarithm, so it goes in exponent times x, and then this is just a simple equation to solve, and you get that d is some constant, let's say a, plus x times d to the -2, because when you integrate, you get 1/2 here, well, and then you just square it. But that is just the x part of D. So the whole D is some function of y, p, q plus x times some function of y, p, q. So we just solve the x dependence of the only metric coefficient we have left. So that was the first step. Then second step, of course, I'm not going to do everything because it's quite straightforward and it's not that difficult. Now we don't really have to solve differential equations. We just plug in for derivatives. So I take this equation. Now I don't solve for D, I solve for just A and B. 2D d y equals 0. And I want to solve this also. So I want to solve, I just plug in my solution, which depends on two unknown functions. I want them to satisfy this, and I get that for it to be true. For this, then I get two equations for A and B. And then I will continue to the next step. I solve A and B with respect to y, and then I want to solve with respect to q, then in the end with respect to p, and in the very end I want them to satisfy these two equations, which are sort of outliers which look different. So that will be like 4 or 5 steps of the calculation, but at each point you just, then I will now, what I will do is I will just know that second derivative of a with respect to a is 0, so I will just write a as APQ plus new constant CPQ times y and x b pq. And now I just want to solve all the q equations and then all the p equations. So let's say I do that, I do everything, and then the last step I will get the full solution. In this form, C5 times Q plus C6 times XP plus Q. So this is the full solution to the Einstein vacuum equations for this metric. So what does that mean? Well, it means that we have a special relationship between the metric structure and the Monge-Ampère equation. So we picked out a special R to the 6th class of Monge-Ampère equation for which the metric structure it induces solves the Einstein field equations. So we picked some special classes of Monge-Ampère equations from the whole class of Monge-Ampère equations. And the scale relation is given like this: minus 24 C2 times C4. So it is a constant. But yeah, that is one thing which I forgot to say. For this solution to satisfy these last two equations, I actually get a condition that this has to be 0. That all these coefficients are not independent. You can solve for one of them from this equation. So this doesn't solve the 10 equations on itself. It solves the 8 of them, and these last two are solved if and only if this is 0. Yes, so just
Ricci tensor is 0.
Yeah. This also has to be 0 from the fact that it is a vacuum Einstein equation in 40. So this also has to be true. So the possible application to that would be that for the special type of metric, for the special type of Monge-Ampère equation, which looks like this, which are used in this 2D incompressible flow, we pick a special class where this D has some structure which have the property that the induced metric satisfies Einstein field equation. Yeah, but we're not quite sure what it means in the physical sense, because we're like in the applications, we're just trying to do what we can with this metric structure, and then to think about the application would be the next step. Or
And by the way, if you just keep the two terms, the d times the determinant equals e, then it looks like,
of course, there is an ambiguity when you look at it like that, because you can rescale both e and d and just keep one constant.
yeah, which looks quite weird.
I agree, because so it looks even weirder because look at the metric that you have. It has only d inside.
Yeah.
The metric at all doesn't depend on the d, so it just the equation looks like this.
So that looks like it makes no sense, right? Because when you take this equation, then just by rescaling, you either make it or break it, which is, it just looks like it has nothing to do with the equation itself, right?
What do you mean break it?
Well, because
you can change the equation.
if the d is not in that form, then I can divide both sides of the equation with something that will make it into that form.
So once again, you assume generality.
Let me. Well, I can do this. Now multiply it by anything in that form. So, without any connection to whether this satisfies the condition or not, by some simple rescaling, I have made an equation that satisfies that condition. So and the solutions are more or less equivalent. So that looks like it has nothing to do with the solutions themselves.
Yeah, but we didn't say that. We didn't say that the solution to the equation itself needs to be assumed for something to hold. That I don't say it's reasonable or something. Yeah, we didn't comment on that at all. Yeah, but we simply start with some equation, and then we just more or less jump to the at least from our point of view, jump to the geometric structures and study them.
But then I don't get the point of taking the equations at all, right? Because those two equations need to be equivalent in some sense.
Wait, which two? You mean the Ricci and this?
No,
you mean these two?
These two.
Yeah, well, so the point is that
So the solutions are tending to something.
Yeah, no, they're not saying that the metric will have the point.
what we're just saying is that this is a class of Monge-Ampere type equations, which gives rise to this metric, and then we completely forget about this equation, right? And then we just study the geometric structure which arises from this setup, and we look at some properties of this geometric structure, like its determinant, its eigenvalues, and its Ricci. Well, you can just write down how the Ricci tensor looks like, but we also try to solve for it being zero. And some of these things are used in the application, some of them are not. And then if you want to compare it with the equations, then of course you have this ambiguity with the E. But yeah, we don't know how to solve or how to interpret it, I guess. At least I don't know, because of course it looks like you can just divide things and push one things into the other.
Well, from my very simple point of view, those equations are just the same, except for cases where d equals 0, which we told that it can't be equal to 0.
Yeah.
So these two equations, from my very simple point of view, are exactly the same. And now you have provided some additional structure that depends on how I write the one and the very same, which looks totally weird because the way how I write it, that's just something that I have in my mind. It's something I write on paper, but there's
so
the one equation that should generate the one structure in some way. And I'm just writing different representations.
yeah, I understand. You can just forget about this equation and focus on the alpha.
Oh, well,
Yeah, so they investigate the geometric structure on its own right. They don't care about this.
So in other words, you could just start with, because if you start with the that has f equals, let's say 1, yeah, or 0. So those are called Hessian structures, and they are interesting by themselves. And we just noticed that it's, in this case, it's a special example of, I mean, like, of something which is more general.
And of course, this is sort of the general because the A, B, and C are.
Yeah. So we don't say this is the most interesting case and nothing else works. Yeah, we just found something that works. Yeah. And now the question is, for example, if we have more complicated, I mean, like ABC non-zero, for example, or at least one of the ABC.
You can always choose E to be 1 and just don't care about it
Yeah.
at all. And you will still have some application to that geometric flow case.
so yeah, but I get that you just write down the equation and then immediately throw it away. I get it, but
So yeah, now yes, but I was going to get how we can involve it soon.
Yeah. Because there is some, until some point, you just can forget about the equation. But at some point, if you use it, then you get some further results, which are not obvious from the beginning. And you have to assume that the equation is
Yeah,
satisfied.
so
just one thing that bugs me is that now it looks like there is one equation that generates pretty much any structure, or maybe not any.
What do you mean?
Yeah, I mean, you should think that A, B, and C are there. It's just, they're just looking at the simplest case. But in general,
okay, so I would think about it like this, maybe that you have this one form and and you have classes of these two forms which generate you this equation and they generate you this metric. So the one form is the building block with J. Yeah. This differential form is the building block that generates you both of these. And of course there is some freedom, right?
Yeah, so this is a good point.
Okay, so we are
the two form.
we are caring about the two forms.
Yes.
We don't care about the equation.
But you see, if you have the two form, you automatically have the equation at your disposal. So it's like you don't have to care about the equation, but it's there. And then the question is, which we haven't tackled yet, yeah? But the question is, if you know something about the equations, can you say something about the geometric structures? Because sometimes you can, already it's known. Yeah, we don't know whether we can use it here. Because as I mentioned in the beginning, the applications of the scalar curvature to the to the vorticities, yeah, of the flow. For example, they do not tackle the problem of the different representatives of the equations at all. Yeah, they just pick some form which represent the equation and then they derive the structure and do something useful with it. So it's possible that some of the constructions are, for example, not invariant with respect to the different representatives. I mean, like different differential forms which give the same equation. And then there is a question. I mean, like, what does it mean actually?
Okay, so we just work with the form and we and the equation is just sort of part of that.
In a sense, but I mean, it really depends at which part of your thinking you are. At some parts, you just can completely forget about it.
Yeah, so
some other parts you can use it.
I wanted to talk now about, so what we have done now is whatever we wanted to derive for G, which is a symmetric tensor on T star, right? So it's a 4x4 matrix. So now we go to the case where we involve the equation, where we have this Monge-Ampère equation in the whole for ABC non-zero, and we pick some section, or we pick some f which satisfies this equation. So I'll write it, for example, like this. And if we do so, then we can.
This looks really much like it.
No, start on the upper left.
Yeah, and up to it like this.
Yeah, that's okay. Just go down.
Okay.
Just run for upper.
Oh, okay.
This is the best alpha you have.
Thanks. So what we can do now is study the metric on the solution. So by pulling back to the base manifold.
Or viewing the metric as being restricted to the.
So instead of here, we get some F star G, which is on just M, symmetric to tensors on M. So that just means that we identify P with X, we identify Q with Y. So if you write this metric in terms of a symmetric tensor, then you would have, for example, here we would have B, X, Y, B, Q times B, X, B, P. And then you would just have to pull this back, and calculate how this would look. So I'm not going to do that fully, but it's not that difficult. This first part are only multiplied with dx dy. So if you pull it back to the base manifold, nothing happens. So you get 2c minus 2b. So now we're on the base manifold. So our metric will be 2 by 2 matrix, symmetric matrix. And it can be written in this form. So if you do everything, then these contributions coming from here would be proportional to the Hessian of the section you choose or the solution you choose. And so this is nice. So again, we study the same properties. So when is this symmetric? When is the determinant? Well, it is symmetric, so that's fine. And now we want it to be non-degenerate, so we calculate the determinant of this. And in 2D, it's quite simple. It also is linear, and you get 4 times AC minus B squared times 4 plus for the determinant of Hessian of F. And this actually is equal to something that we have seen before. This is 4 times the factor of alpha. So that is the result for this metric. So, again, okay. So
Start from the top right.
So why isn't there cross terms? I mean, there should be like something C times FYY. Yes, A times Fxx.
yes, that is because you are thinking about just this equation, and these terms are here in. Oh wait, no, this is wrong. Yes, sorry, you're right. So here you have 4D times either both things. So Fyy plus 2B Fxy x plus D times determinant. So this is the full thing. 4D times this. And this is 4 times AC minus B squared plus 4DE. So the whole equation, the full equation, had not only this term, but also C times this, 2B times this, and A times this, and it adds to the E, which was on the right hand side of the equation. So it should be minus.
But now we assume now that the equation holds.
Yeah.
Now in this case, when we are in 2D, we are using the equations of motion. So other than the Monge-Ampère, and that's important. And so we get some nice result that the determinant is determined by this Ampè, which we assume now to be non-zero. In the 4D case, we didn't have to have Ampè non-zero. The only thing we had to have non-zero was this D. But now things are different. If we use the equations of motion, if we pull back, then the path here has to be non-zero. We can calculate the eigenvalues. Given simply by C plus D plus D times Laplace of F plus minus square root of So these are the eigenvalues, and sorry, C plus A. Yeah, if you're missing B here, then B is in here, inside. And yeah, we didn't know how to see what's the signature here, right? Or did we calculate the signature here? I don't think so. If it's 1, 1 or 2, 0.
Not sure, but I don't think it's easy.
Yeah. I don't think it's obvious. No, because it depends on the F. Yeah, it depends on the F, so that's why we do
margin. So what is the relation, or is there a relation between the four-dimensional metric and rho? I mean, is the metric
No, and not a priori. Not a priori.
not relation with respect?
I mean, or at least it doesn't have to be, and maybe in some specific choice of A, B, C, D, E, it will happen, but we don't know.
Yeah, no,
But there is no
automatically.
There is no general result. That's no.
You check the compatibility between metric.
So better I would say I'm not aware of that there will be result of this kind.
So the next thing to do is to check again the Einstein equations, but now it's a problem, right? Because they're in 2 dimensions, and Einstein equations in 2 dimensions are well, special. So you can compute the Ricci tensor of this thing, but now you have a problem because it's even if you put these to 0, it's super complicated because you have third and fourth derivatives of this f. But of course, you can make your life easier by using the equations, and then you would have to do derivatives of the equations and then try to put them in and simplify everything. We didn't manage to do that, or well, I tried something and it didn't simplify that very much. So even if you would calculate the Ricci tensor, you know that you can just change your coordinates to have a Ricci flat metric, because in 2 dimensions, the metric has 3 degrees of freedom, say like this, and you have 2 deformable of symmetries, 2 change of coordinates, and 1 conformal in scalar.
So maybe now it would be a question from us to the audience that whether our way of thinking is reasonable, that actually it doesn't give us anything interesting if we show that even if we manage to show that these 2D metrics solve the equation, because what would be the result, right? You already know that every metric will solve, right?
In the right coordinates.
And yeah, and
If you allow
and it
every scaling is of a vector, right, function.
Yeah.
If you allow that.
Yeah, and if we don't, then it's super complicated to figure it out, because you have all these derivatives of this, and you would need to use these differential consequences of that. And yeah, I didn't find a nice way to do it.
on the other hand, right, we have for this 2D metric, we have pullback, we have dropped the GR considerations and just looked at the metric structure itself, because it's quite interesting. For ABC equals to 0, we have this multiple Hessian.
Yeah,
And those are
that's what I was going to say now. So the last thing if we skip the solving the Einstein equations due to us thinking it being trivial, then we can put again ourselves to a very, very special case of the metric being just a multiple of the Hessian of the function of the solution. And this is quite a known structure called a Hessian structure or Hessian manifold, which we found some literature on, and it is also used in the applications. And it turns out that I was looking through some of the references of Hessian structures, and the only thing you need to do to calculate the Riemann and Ricci tensor is not the full Christoffel symbols, but you are just interested in this contraction of the Christoffel symbols.
So A equals B equals C.
Yes. And you are just interested in this contraction, and this is nice because it can be written by this formula, derivative of the logarithm determinant of the metric, which our metric is this star G times dx. But we have an equation precisely for the determinant of the metric, that is the Monge-Ampère equation, and for this case it's equal to 2p. So we can just plug that in, or we can rescale e and say it's just 1e, and this is just logarithm of e dxy, and the Ricci tensor, according to this formulas from the results of the Hessian structures, is just given by the derivative of that contracted Christoffels. Therefore, these special types of metrics, the formulas simplify this way, and that is just 1/2 the logarithm e over dxi dxj, which is again the Hessian of the logarithm of e now. So we return back to from starting with the equation that Hessian determinant of Hessian of f is e, to the Einstein equation, which is that Hessian of the logarithm of e is 0. So if we for example do just one thing, if we do determinant of this, then you get an equation that 1/2 determinant Hessian logarithm of e. Okay, if we want the Einstein equation, which is this, we do determinant of that. So that's the Einstein equation. We get back e here. So this is the determinant of the Einstein equation. So if you do it like that, you get this weird equation for the coefficient of e, which is the only.
This is one comment.
Yeah.
This is not the Einstein equation. This is the equation for the manifold V in Einstein.
Yeah,
It's not
yeah.
the same thing, correct?
Yeah, it would be the same for lambda being. Yeah, no, it would be if there was 1/2 r here.
Yeah, this is the condition for
Einstein
manifold.
yes.
But we know that if G is Einstein, then it solves the vacuum field equation, right?
Well,
It depends on the dimension and
Yeah,
the constant.
it's about the same.
In 2D there's
The
some
usual Einstein equation is not.
but I think in 2D
That's it.
the dimension works out in such a way that it should solve for.
Let me ask you something else. So the alpha, if we take the 2 for alpha
Yeah.
to be the fundamental thing that differentiates, then it's clear that there's a difference between the equation where you rescale everything or whatever. So does alpha have any nice extra properties when D is of the form that you wanted?
Oh, I see. Yeah, we didn't look at that. You mean of this solution?
Yeah.
Yeah, we didn't look into that. What would that mean for the alpha?
Because it seems like you have more control over things. The equation is kind of you have multiple things, but alpha is
We can look at like the row of it and stuff like that. What other structures would that?
Sure. So that's actually the result of the last like 2 weeks, and there are many natural questions that we didn't manage to even look at. Yeah. So for example, if you check f star g, maybe just to note for redirect, especially if you consider the equation gamma k ki equals something, then this is a one equation from the community around the hashing structures. But the other equation that follows, it's not automatically. I mean, it's possible. So, of course, we have to do some further study of the papers that are already known here. But that's not automatic that you have this special kind of gamma k ki in our case, which is only if you assume the equation to hold, which, you know, like the hashing structure is considered usually just by itself. It's some special kind of memory. Yeah, and you study the properties.
Yeah, and we basically have a hashing structure, and we can use all the things that they know, but we have a special condition for the determinant of this structure. Yes. That it should be the E because that's the Monge-Ampere.
So we have sort of a special F or special subfamily of Fs that gives rise to hashing structures. And the second comment is if you check the F star G, which is about the number 4, so this is this general guy, then we can pick A, B, C, D, so that this 2C so that this matrix is also hashing of some other function, which doesn't have to satisfy the Monge-Ampere equation itself. And then we have some nice deformation of the hashing structure. And the question is, for example, whether the results which hold for the hashing structures will also hold for these kind of deformations.
Yes, so that was like the point that if we restrict to ABC equals 0, then we get the hashing structure, but if ABC is not 0, can we view this as just a deformation of the hashing structure? No, not really, because you would have to have this to be a hashing of F, right? So which I guess is not solvable for the most general ABC, but if you get some additional conditions on ABC that there exists some F that this is a hashing of that F, then you just get a deformation of this hashing structure, which was also one of the things that they considered in the literature. Yeah, so we just try to follow like things that we can actually calculate, and then we try to interpret them, but maybe some of the interpretations are not that accurate.
So it should be obvious that it's sort of I mean, like naive beginnings of some research project that we just thought, okay, we have some metrics which arise from maybe not completely expected direction, and whether we can do something with them. Having in mind that already some applications are.
Yeah, it was like a hope that a lot of the people who work in this, they use some special cases and very restricted Monge-Ampère equations, and if we just try to work out everything in the most general sense, or where we can, then maybe they can also apply it in their special cases by just picking special ABCD and looking for what we did. And yeah, because the signatures and some Ricci scalar curvature and scalar curvature are used in some senses. So if we give some general results for there, they can just pick ABC, which they use in their models, and apply ours.
Could you turn it around? Let's say you start in 2 dimensions. You have some metric ABC, and there's some interesting maybe structures of this metric along these lines. Now the question is, can you find the D so that you can make this 4D system out of this 2D geometry?
Yeah, that's a good question. Yeah. Can we arrive to the equation in the end?
Yeah, good question. Not know.
Yeah, we didn't look into that, but sounds interesting. Yeah, maybe it might be more difficult, because if you just go from the 4D and you just put some section of the bundle and pull back, then it sounds straightforward. But if you want to lift something back to the cotangent bundle, that sounds like there may be some abstractions to do that in all the case.
Could be, but don't worry about those things in the first place. There's something interesting.
That's true. Yeah. Okay. So I guess that's everything. Just to to summarize is that if you have these Monge-Ampère equations, then there is a lot of different structures. So Radek said you have these complex stuff and product structures, but we were mostly interested in the metric and loosely guided by some work that was done by collaborators of Radek. We tried to calculate as many things as we can with this metric. Of course, we had to simplify in some cases because computations were too difficult, but we managed to find some solutions. Now we try to interpret them with respect to these applications and see if we can do something more. So yeah, that's everything. Or if you have something more to say. Okay, then thank you very much for listening. And of course, if you have any questions or want to talk after that, we'll be here. Thanks. What's the recording?